All right, here is the second example we're going to have a look at. This one here, I've got a hyperbola with the two curves, one here and one curve here, and a straight line thrown in the middle. And at the moment, it has a y-intercept of 0. There it is. So it's going to be like plus 0, minus 0, whatever you want to call it. And what we're wanting this to do is to find out when this line with this gradient can have only one point of intersection with this line and only one point of intersection with this line. And for that to be true, we're going to have to find out what would the x values, what would the plus k, what would the y-intercept be in order for this to have one point of intersection. Here it is, look, one point of intersection. There ooh, that's not very good, isn't it? Okay, there it is. And here it is, over here, same deal, yeah? One point of intersection, keeping the gradient the same, there it is. Gradient, is that the same? Ugh. Not really, but one point of intersection. So where is this going to be? Where is the y-intercept going to be if the line touched there? That line was moved down so it touched there, or moved up so it touched here. What would the points of intersection be? What would the y-intercepts be? That's what we're going to discover. All right, let's go ahead and see if we can do that. So to do that, we're going to first of all write out the two equations and make them simultaneous. So I've got y is equal to 1 over x minus 3, and I've got y is equal to negative 1/3 x. And I'm going to put plus k on the end because k is going to be the intercept, but we don't know what it is. So we're going to let the equation do the heavy lifting, and we're going to use the discriminant function as we go along. And the reason we'll have to use the discriminant function is, as you see, as this plays out, we're going to end up with non-numeric values as coefficients of either the x squared or the x to the 0. So let's go ahead and see if that's the case. So first job is to make them equal to each other. So I'm going to go negative. In fact, I'm going to rewrite this. I rather like it as x on 3. Negative x on 3 plus k is equal to 1 over x minus 3. Much nicer way of saying it. It's got slightly less components as well if I do it that way. It's because I've got the x now as part of the numerator. So first job, I don't like the fractions. Let's get rid of the fractions. So first I'm going to multiply everything by 3, and that will get rid of this one here. So I'll put a 3 there, I'll put a 3 there, and I'll make this times 3 on top. And so suddenly this divided by this will leave me with a negative x, plus I've got a 3k, and equals, and I've got 3 over x minus 3. Now I can get rid of this by going, let's multiply everything by x minus 3, and I'm going to multiply all of this by x minus 3. Here it goes. So I'm going to have x times negative x, that's going to be negative x squared. I've got a negative 3 times a 3k, it's going to be negative 9k. What else have I got here? Oh, by the way, that divided by that is 1. I've got a 3 left on that side, mustn't forget the 3. Then I've got a negative x, and a negative 3x is going to be plus 3x, and I've got a 3x and times an x is going to be plus 3kx. It's a 3k times x is a 3kx. It's a k there. Does that look like a k? That's not very nice. Okay, let's get that. So it looks like a k. So it's going to be 3kx. There it is. Okay. Hopefully that looks a bit better. Sorry about that. All right. Now we're going to subtract that 3 from both sides, minus 3. And we're doing it because we want to make it equal to 0. In order to be a quadratic and to solve a quadratic, we have to have it equal to 0. Well, let's tidy this up here. It's looking a bit like a dog's breakfast, really. So it's going to be minus x squared. Now we want to make this so it's going to yield a coefficient of x. So we've got an x and an x. So I can take the x out. There it is. Okay, and this is going to be a 3 times x makes 3x, and 3 times k times x makes 3kx, or 3, yeah. So 3 times x is 3x, and 3kx times 3 is correct. Minus 9k minus 3 equals 0. I got a lot of minuses in there. I could just multiply everything by negative 1. I'm going to avoid that and just leave it the way it is. I think that it's going to work perfectly fine. But let's identify a few things now. I can see the coefficient of this is going to be, so the a value is going to be negative 1. And the b value is going to be the coefficient of x here, which is 3 plus 3k. And the c value is going to be everything else, minus 9k minus 3. Now, the challenge, of course, here is quite often you end up having either this term or this term or this term with a non-numeric value, for which we need to use the discriminant in order to resolve. However, we don't have this in this case. We've actually got two values. We've got the b value with non-numeric values, and we've got the c value with non-numeric values. So we've got a bit of a double whammy here. We're going to have to use the discriminants and see how this plays out. So I'm going to use b squared minus 4ac, and I'm going to make it equal to 0 because we're wanting to find out when there is only one point of intersection, either with the line here or the line here. We don't want 2 points. In other words, if it was up here, then we're going to get 2 points of intersection, yeah? We don't want 2 points. Or if it's down here, for example, we would get 2 points of intersection, like here, and so here. We don't want 2, we only want 1 point of intersection. So let's see where that would fall. So let's substitute these in. Let's populate the expression, or the equation in this case, with these equal 0. Let's look at b. Well, b is going to equal 3 plus 3k squared. So it's 3 plus 3k, there it is, minus 4 times a, well, a is -1, times c, well, c is -9k minus 3. And I put that in brackets because it's probably just a bit more handy to do it that way. Let's expand this out. Well, 3 times 3 is 9. 3k times 3k is going to be 9k. Then I've got a 3 times 3k is plus 9k. Another 3 times 3k is another plus 9k. Now I've got minus, so it's going to be plus 4 now, times minus 9k minus 3 is equal to 0. Okay, so let's resolve all this. Well, I've got a 9, plus I've got 18k. This is 3k times 3k. It's 3k squared. Almost got caught out there. 9k squared. Okay, plus 4 times -9 is going to be -36, so I might as well just make that a negative straight away. Then I don't have to mess around with it. -36k, and 4 3 is going to be 12, so minus 12. And that all equals 0. All right, let's simplify the whole thing a bit. So I've got a 9, which we'll just leave there. We've got an 18k minus 36k makes 9 is 18k. So we've got rid of that, we've got rid of that. We've got a plus 9k squared minus 12. So we've got a 9 and we've got a minus 12. So that's going to yield a -3. So let's go ahead and tidy this up. So I'm going to end up with that all equals 0. I've got a 9k squared. A 9 minus 12 is going to be a -3 on the end there. And then I've got a minus 18k in the middle there. And all of that is equal to 0. Well, I can divide everything straight away by 3. So let's go ahead and do that. So divide this by 3 and divide everything by 3. So this now becomes this by 3, this by 3, this by 3, and this by 3. So this becomes 3k squared minus, that will be 6k. This is going to be -1 is equal to 0. So let's have a look. Well, that doesn't work well. So we can't actually do anything with this. We're going to have to find a way to find the values of k. So I'm going to use my calculator here. I'm going to just go straight into using the quadratic solver here. And let's see where we end up. So I'm going to go menu. Let's go 8, 2, 1, and let's see what we've got. So I've got, from previous calculation. So this one is a 3, it looks like. I've got a -6, and I've got a -1. And where do I end up here? So I got solve that. All right, so I've got 2 values now. And my 2 values are, the first one I'm going to use is 2.1547. So I'll put either k is equal to 2.1547, or k is equal to, and I've got -0.154. There it is, and I'll just bring it down. Actually, here it is. -0.1547. 0.1547. So they are the 2 values for which this is going to touch at just 1 point. Let's see if that makes sense. Let's have a look at the diagram here. In fact, I'm going to choose a fresh diagram. Here we go. So let's just see if that makes rough sense. And part of the thing of doing this is to say, does that look about right? And I think that's a reasonable way of doing this. So first of all, let's look at the upper value. And we're going to have a value of about 2.1. So here we've got our line. If we drew the line up a little bit, it's going to be somewhere around here. So 2.1. So here that's 2. 3 is going to be there. So I think that looks about right. Let's have a look. So 2.1-ish. So it's going to, it's going to go like here, and it's going to end up somewhere in about there. So that is the value there. And that looks like it's about 2.1547, about 2.1, about there. This one here, though, looks like it's going to be, let's try and make that as accurate as we can. So I'm just moving stuff out of the way here, so let's see what we got. So if I was to draw that, keeping the gradient the same. Again, this is not very good. You can see the lines actually starting to converge here. It's getting closer and closer. But there's our point of intersection. Here's our point of intersection, more or less. And let's see if that makes sense. So we've got, it's going to be negative 0.15. Well, there's 0. There's negative 1. So it's about negative 0.15. That makes rough sense. I think we're about right there. So let's say the k value here, the y-intercept is going to be 2.1547, and the value here, the lower value that is going to equal it's negative, of course, 1547. And that's what we have found. So the intercept, the y-intercept, would be, for the lower one, that line there you're seeing would be negative 1/3 x minus 0.1547, tacked on the end there. And this line here is going to be negative 1/3 x plus 2.1547. We add the plus on the end and the 2.1457. So that is what we have found.